Assalamualaikum warahmatullahi wabarakatuh. My name is Anis Nazira binti Shamsuddin, and today I will be presenting my discrete mathematics assignment. Our topic focuses on relations, function, and graph, and their critical application in computer science. To understand the advanced system we use today, we must first look at the most basic foundational. What exactly is a relation? In discrete mathematics, a relation is a mathematical framework used to establish a link, an association, or a connection between elements of two entirely different sets. Imagine a set of students and a set of library books. A relation simply tells us who borrow what. In its most general form, mathematical relations are incredibly loose and flexible. There are no strict laws. Any single input from the domain can relate to multiple outputs, or even no output at all. While this flexibility is perfect for theoretical mathematics, it introduces a lot of chaos if we try to program it directly into software. It just maps raw connection without any order. Now, why does this matter to us in computer science? While general relations are great for abstract math, computer systems require absolute predictability, structure, and optimization. We cannot have a system that guesses outputs. Therefore, computer science utilizes special cases of relations, specifically function and graph, to enforce strict rules that keep software, database, and networks running smoothly. Let's explore our first special case, which is functions. In pure mathematics, a relation strictly transforms into a function only when a specific rule is met. Every single input in the domain must map to exactly one unique output in the domain. An input cannot branch out into two different results. This exact mathematical restriction is used to design relational database management system. Using things called schemes and tuples, look at the student's table displayed on the slide. This scheme defines the columns, and each row is a tuple. Here, the column student's ID acts as a unique identifier or a primary key. Because of functional mapping, student number 1 can only point to Alice Smith, and ID number 2 can only point to Bob Jones. This rule guarantees that the database never mixes up students' profile or create duplicates, corrupted identities. Now, let us break down the mathematical process of how database verification checks this. Let's say our system is given a relation set containing order pair 1 Alice and 2 Bob. To verify if this data structure is safe and qualifies as a valid function, the system runs a mapping check on the domain set, which contains the input 1 and 2. Step 1. We isolate input 1. We see that 1 maps strictly to Alice. That is exactly one output. Step 2. We isolate input 2. We see that 2 maps strictly to Bob. This is also exactly one output. There are no duplicate input in our set pointing to different names, which means no single student ID belongs to two different people. Therefore, we can mathematically conclude and prove that this database relation strictly satisfies the definition of a function. Our second special case shifts our focus from data storage to network connectivity, and that is graph. In discrete math, a graph is a specialized geometric and structured representation of a binary relation that acts on a single set. Instead of using standard boring text lists, a graph allows us to visualize connection. As you can see in the diagram on the right, the elements of our relation are treated as vertices, which are the circular nodes labeled A, B, C, and D. The actual relationships between them are modeled using directed arrows called edges. If there is an arrow from A to B, it means a data path or a physical network cable exists between them. This structural case is highly valuable for mapping things like fiber optic internet cables, flight path, or social network connection, where users are nodes and friendship are edges. Let's look at the computational process. Computers only understand numbers. To solve this, the visual relation set, which consists of the directed pairs AB, AC, BD, and CD, must be translated into a binary adjacency matrix. So let me guide you through how this matrix is constructed step by step. First, we create a grid of our nodes from A, B, C, D to A, B, C, D. If a direct error exists, we input a value of 1. If no error exists, we input a 0. Let's look at a row A. There is an arrow pointing from A to B and A to C. So, under column B and C, we write 1 and the rest are 0. Now, look at row B. There is only one error leaving B and it goes straight to D. Therefore, we place a 1 strictly under column D. Next is row C. Just like B, it only connects directly to D. So we place a 1 under column D. Finally, look at row D. Node D has incoming errors but zero outgoing errors. It is a dead end. Therefore, its entire row is filled with zero. This final binary matrix of ones and zeros is what a computer CPU reads to instantly understand the structure of a massive network. By combining these structures, computer science solves massive real-world problems. Relational database use functional mapping to manage terabytes of user data cleanly without errors. Meanwhile, network infrastructures and routing protocols use graph relations alongside algorithms like GSTRUS or flight marshal to instantly navigate matrices and compute the shortest path for modern internet routing and GPS applications like Google Maps. To bring everything together, let's look at a conclusion paragraph on this slide. Relation, function, and graph are undeniably the mathematical backbone of modern computer science. By constraining loose general relations into highly predictable mathematical structures, we successfully bridge the gap between pure abstract mathematics and practical software engineering. Functional mapping acts as a shield that guarantees absolute data integrity within our database management system. At the same time, graph-based binary matrices act as a map that enables routing algorithms to instantly compute the shortest path across global digital networks. To put it simply, modern software architecture, secure database portals, and intelligent satellite navigation systems will quite literally not exist without the mathematical theory of relations.